Page 10 of Euler's Complex Numbers, Chapter 16, HL. So now we're finally going to use Euler's form. And if you remember from the investigation, Euler's form is a very compact and, I wouldn't say intuitive, but a facilitating way of writing cosine theta plus I sine theta, because the rules of multiplying together cis theta with other numbers are summarized in the rules of exponents, as we'll soon remember. So if you have the complex number z, it can be written as modulus of z times cis theta. And in Euler's form, you could write that very compactly as e to the I, oops, I forgot the z. Z magnitude modulus e to the I theta. So let's write 1 plus I in polar cis form. That would be a triangle at 45 degrees that is hypotenuse square root of 2. So we'll write square root of 2 cis 45 degrees, or instead of 45 degrees, I want to write that in radians, so I'm going to put pi over 4. And Euler's form, it would be square root of 2 e to the I pi over 4. So now let's use e to the I theta equals cosine theta plus I sine theta to find the value of e to the I pi. Okay, so that would be cosine of pi plus I sine of pi. And cosine of pi is equal to, according to the unit circle, it's equal to -1. And sine of theta, according to the unit circle, is equal to 0. So, there we go. Isn't that the beautiful equation? E to the I pi equals -1. C. Let's find the value of e to the negative I pi over 2. So that's equal to the cosine of negative pi over 2 plus I sine of negative pi over 2. And if we look at the unit circle, negative pi over 2 is pointing straight down, so the cosine of that is 0, and the sine of that would be -1. So it would be -1i, and so basically the sum of that is -i. Let's look at 2. Use cis theta equals e to the I theta to prove that cis theta cis phi equals cis theta plus phi. So we could put cis theta equals e to the I phi, right? So cis phi is equal to e to the I phi. So we could take this left side, which is cis theta cis phi, and we could rewrite it as e to the I theta times e to the I, that's supposed to be an I, phi. And using the rules of exponents, we can just add those exponents together. So e to the I theta plus I phi, which is equal to e to the I theta plus phi. And so if we could convert back our e to the I to the theta plus phi into cis theta form, we just write cis theta plus phi. And now we're done. Okay. Number 3. Suppose z equals cis theta. Find the arguments of square root of z. So square root of z, remember, can be rewritten as z to the 1/2. And z in this case is cis theta. Remember that cis theta can be rewritten as e to the I theta. So if we wanted to, we could rewrite z to the 1/2 as e to the I theta to the 1/2, which is equal to e to the I theta over 2, which is equal to cis theta over 2. So it's theta over 2 is the argument. What about negative IZ squared? Okay, so that would be negative I times, and remember Z is cis theta or e to the I theta, so let's say it's e to the I theta squared. So that would be negative I times e to the I 2 theta. And negative 1 could be rewritten as e to the I negative pi over 2. Because negative I is pointing straight down, right? And then we have here e to the I 2 theta. And so now we can combine the exponents by adding them together, and then we would get e to the I 2 theta minus pi over 2. So the argument would be 2 theta minus pi over 2. Let's do 4. It says to evaluate e to the I. So e to the I is equal to e to the I times 1 radian. So that would be equal to the cosine of 1 radian plus I times the sine of 1 radian. So let's use the calculator to figure out what the cosine of 1 radian is. It's going to be about a half, 0.540. What's the sine of 1 radian? .841. Okay, so that's not nice at all. What about I to the I? Let's see. Let's first of all write I as Euler's form. And remember, I is a vector in the complex plane, which points straight up. So it would be ei pi over 2. And that would be taken to the ith power. And now we can multiply the exponents together. So we would get e to the, and I squared, remember, is negative 1, so we get e to the negative pi over 2. And that's just some real number. So put e to the negative pi divided by 2. 0.208. It's just a real number. Okay. And now let's start talking about de Moivre's theorem. Use polar form to calculate z cubed. Okay. So z cubed, so polar form would be modulus of z, e to the I theta. And if we wanted to calculate the cube of that, it would be z, you could put z cubed pi, or you could put z modulus cubed, either way. And e to the I theta would be e to the I 3 theta. E to the I theta would be cubed, right? Another way you could write it would be modulus of z cubed and cis theta cubed. And remember, when you multiply cis thetas together, you end up with adding the arguments together. So it would be z cubed cis 3 theta. Okay, so it's similar to the 3 theta here, goes with the 3 theta for that too. Okay, so there's different ways to write z cubed in Euler's or in cis theta form. I guess they wanted to know cis theta form. So we could write here that the nth exponent of modulus z cis theta is equal to z cubed times cis, not cubed because it's n, right? Cis n theta for all rational n. So the key step of the math induction proof of de Moivre, if we look in the page 498 reading, we're not going to go through the mathematical induction proof, but just to tell you what the trick line of it is, I think it's the line in the step case where they just did the substitution of the pk case. So they got that in there, and that's multiplied times z cis theta. And then they look at this and they say, oh, when I multiply together cis thetas, I add the arguments. So then they take k theta plus theta, and basically they make it into k plus 1 theta. And of course, the modulus are all just multiplied together k plus 1 times. So I think that's like maybe the trickiest part, but that's not a really hard math induction proof, in case someday someone asks you that. The theory is proven using math induction for all, using math induction, they prove it for all positive integer n, so like z plus, okay? It is also true for rational and negative n, okay? And in example 19, they show you how you prove those, okay? It's just an extension of proving it for positive integers. So here it says to prove de Moivre's theorem using Euler's form in the law of exponents, and this is a lot easier than using math induction. So basically, de Moivre, remember, is this here. So we have z cis theta to the nth is equal to z to the nth times cis n theta. So let's take the left side, and we'll look at it in terms of Euler's form. So that would be z. Instead of cis theta, we're going to write e to the I theta, and that's to the nth power. And that's equal to z to the nth power, e to the I theta to the nth, and we're just going to write it together in the same exponent because we just multiply it, right? Now that we have it written like that, we could just rewrite it using cis theta form, which would be like that. And we're done before we even started. Maybe to make it a little bit more exciting, we could have written, before we wrote this step, we could have written z to the n, e to the I theta to the n, and then maybe come back and written that. That would have been a little bit more exciting.